Section 6.1, Multivariable Linear Systems and Row Operations. Key concept, operations that produce equivalent systems. Each of the following operations produces an equivalent system or linear equations. Interchange any two equations, so you could switch A and B. Multiply one of the equations by a non-zero real number, so we can multiply the first one by 3 if we wanted to. Add a multiple of one equation to another equation, so we can add these two equations together, we can even subtract them. Write the system of equations in triangular form using Gaussian elimination, then solve the system. On the first step, we're going to take 3 times what I've called equation A, and then we're going to minus B. So we take A times 3, we get 3, 9, 6, and then 15, and we can subtract the second equation because that'll make, we'll have 0x. So we're eliminating x. Then we get 8y plus 8z, because we have 9 minus 1, 6 minus 2, 6 minus negative 2, and 15 minus 7. So we have a little bonus here that we can divide everybody by 8 and get y plus z equals 1. Then we can take 2 times a and subtract from c. That way we eliminate x again. So when we multiply 2 times a, we get 2, 6, 4, 10. There's a 2, 6, 4, 10. And we're going to subtract c. And we get 6 minus 2 is 4, 4 minus 3 is 1, 10 minus 3 gets you the 7. Well, now we have to eliminate one more variable. And I noticed that if we take this top one, or this one right here, minus this equation, we get 0z. So when we subtract these two, we get 1 minus 4 is negative 3y equals negative 6. So we discover that y equals 2. Well, now we have to plug back into one of these. Probably be easy to plug 2 in here. We get 2 plus z is equal to 1. So when we minus 2, z is equal to negative 1. Well, now we got to go back to one of the originals. This bottom one is good as any. And we got to plug 2 in for the y. That makes this 4. So we have 2x plus 4. And then we plug negative 1 in for the z, which is minus 3. And that's equal to 3. So we have 2x, that's 1, so plus 1 is equal to 3. 2x now is equal to 2, so x equals 1. So the answer is 1, that's the x, the y is 2, and the z is negative 1. A matrix is in row echelon form if the following conditions are met. Rows consisting entirely of zeros, if any, appear at the bottom of the matrix. So we're down here at the bottom. We have this bottom triangle. This bottom corner needs to be zeros. The first non-zero entry in a row is 1, called a leading 1. So the first non-zero in a row is 1. So that's 1, 1, and 1. For 2 successive rows with non-zero entries, the leading 1 in the higher row is farther to the left than the leading 1 in the lower row. So in other words, we have this kind of triangle effect. Well, we're going to solve these systems. We're going to use matrices instead of leaving the variables. So with the matrices, we just remove all the variables. So we write 1, negative 1, 1, 3, negative 1, 2, negative 1, 2, and so on. So we get this 3 by 4 matrix. Now we're going to use the same process, but I want kind of little notes taken off to the side. So we're going to write row 1 plus row 2, and then this means replace row 2. So we have, if we take row 1 plus row 2, we get this first 0. We want this one to be a 0 first, then we want this one to be a 0, and then we want this one to be a 0. So this one's a 0, we want the second one here, and then we want the third 0 in that spot. Well, if we add row 1 plus row 2, we get 0 in this spot. And then if we take 2 times row 1, so 2, negative 2, 2, and 6, and subtract row 3, we get a 0 in this spot. Now when you do all those computations, you get 0, negative 1 plus 2 is 1, so there's the 1. 1 plus negative 1 is 0, and 3 plus 2 is 5. Then when you work with the third row and replace the third row, you get 0, 1, negative 1, 2. Well, now we want the third 0 to be right here, so we can take row 2 minus row 3 and replace row 3. And when you do that, you get this matrix right here. Now what that tells us is that z must be 7. So this says z equals 7. And then if we go up here, we have y plus 0 times z is equal to 5. Well, that's just going to be 0. So now we know y is 5. And then when we go up to the top, we have x minus, let's see, that's going to be y. So minus 1 times y. And then plus z times 1 times z, which is 7. And that's equal to 3. So we have x plus 2 equals 3. 3. So x equals 1. So now we have 1, 5, 7. Let's go over to the other one to the right, and we're going to write this as a matrix. There's all the values. We need this first 0 right here. So we're going to take 2 times row 1, subtract row 2, and then just replace row 2. And while we're at it, we can take row 1 minus row 3 and replace row 3. So we can get our first and second 0 there in one shot. So here's the next matrix with all the values plugged in. And the third 0 I want is right there. So we can just take row 2 minus row 3 and replace row 3. And down at the bottom here, we get 0 equals 0, which is absolutely a true statement. So far we have infinite solutions. But if you have infinite solutions, you have to have an ordered pair, because you can't just have any ordered triple in this case under the sun. Like, you can't just pick any 3 numbers and say, well, that must be a solution. So we start out by just having the z. So if we pick a z, then we have right here y plus 3z is equal to 3. So y must be equal to 3 minus 3z. So we have 3 minus 3z here. And then we have at the very top, I'm kind of running out of room here, we would have x, and then the 2 times y, so we have 2 times the y based on z is 3 minus 3z, and then we have plus z right here, and that's equal to 8. So let's do the distributive property. We have plus, that's a 2. 6 minus 6z, and then plus z is equal to 8. And then we have x, well, let's see, we have negative minus 5z is equal to 2, because we minus the 6 over. And so if I add the 5z, I get 2 plus 5z. So when you have infinite solutions, the solutions are based on whatever you pick for z. You just can't pick any 3 numbers you want. So very quickly, if I were to pick 1 for z, let's say, pick 1 for z, the y must be 3 minus 3, that's 0. And the x must be 2 plus 5, it must be 7. So that's one of the solutions. But I can't pick 7, 0, 5. That wouldn't make any sense. That's not a solution. So let's get started. We're going to make this into a matrix. We're going to take row 1 minus 4 row 3. So row 1 minus row 4 row 3. That'll get a 0 here. And we can get a 0 here by taking row 1 minus 3 row 3. So we get the 2 zeros here. Well, I notice that the second row is all multiples of 5. So we're going to take row 2 times negative 1/5. We get 1, 2, 5, 6. I need a 0 in that spot right there. So 11 times row 2 plus row 3 and replace row 3. And we get that corner to be zeros. But I notice that I can take 1/8 of this right here and get 1, 1, 4. Well, now we have y plus z is equal to 4. So y must be 4 minus z. So let's go on up here and make it 4 minus z. So we have 4 minus z, that's the y. And then, so we have x to get yet. Let's go back down here. And we have this nice corner as zeros. So we have, let's see, where do I have some room here? Let's go down below. I have right here x plus 2 times y. And y is 4 minus z. So 4 minus z. And then plus 5z is equal to 6. So x is equal to 8. Not 8, but plus. 8 minus 2z plus 5z is equal to 6. That's plus 8. So we minus 8 over. So we have x plus 3z is equal to negative 2. And so x must be negative 3z minus 2. So negative 3z minus 2. Negative 3z minus 2. And finally, we got to get the w. So the w is sitting right there. So we have 4w. And then we need plus the x. So plus negative 3z minus 2. Plus 2 times the y. And the y is 4 minus z. And then finally, minus 3z should be equal to 10. So we have 4w sitting here. So we have minus 3z plus 2 minus another 2z minus 3. So negative 6, we have negative 8z. And we have minus 2 plus 8, that is 6. So we need to minus 6. That's equal to 4. That's good because they're all multiples of 4. So w is equal to 2z plus 4. So we go up here, we got 2z plus 4.